are taken in very weak storms, and they're actually taken by the Hurricane Hunter aircraft, which are the operational aircraft rather than the research aircraft. And what happens when you have a weak storm that's just forming is the crews in the Hurricane Hunter aircraft are tasked to find the centre and estimate the central pressure of the storm. So they fly around very low because in a very weak storm it can be quite hard to find the centre. So we've got two things here. They're flying low and these tend to be very weak storms. People haven't flown aircraft this low with one exception, which was the sea blast experiment, which we'll talk about a bit more later. They haven't flown into strong winds at these levels, except during sea blast, since about the 1970s. It used to be that there were three groups in the United States who do hurricane reconnaissance. There was the Air Force would typically fly in as high as they could at 600 or 700 millibars. The Navy, because they were oceanographers, they liked to be able to see the water, so they would fly in very low. And the research aircraft would fly somewhere in between. But the Navy pulled out of doing hurricane reconnaissance in the 1970s from memory, and since then no one's done really low-level flights, except in very weak storms. And if you remind me, I'll talk a little bit about why the weakness of the storms is significant when we get to the dynamics. It's a good question. More data from James. These are the same plots as on the previous slide, but we're now plotting against log of height rather than linear height. Just to show you that, as you'd expect from your boundary layer theory, we're very close to a logarithmic profile. It's actually not exact. There is a very slight departure from it down near the surface, which hasn't been satisfactorily explained anywhere in the literature, but I think is most likely due to an interaction between the waves and the flow.
So just let me make sure that a vertical resolution of observation is about 5 to 10 meters in this.
Yes, that's correct.
Okay. So this is typical logarithmic layers in up to 200 meters above, right?
Yes, probably up to 200 metres. It's always very hard to say where does a layer finish, right. Because it blends smoothly back in, but probably to 200 metres. So having looked a little bit at the vertical structure, I'll just show you a couple of radius height sections. This is the oldest one. This is from a paper by Bill Frank. So we have the maximum updraft in here. We have the strong inflow, weak outflow aloft. And the interesting thing in this figure is the very steep slope of the zero radial flow line. The boundary between inflow and outflow slopes very steeply with radius. This is seen also in, these are rather more sophisticated cross-sections done by Michael Bell and his co-authors. They were published just last year. So these are three in Hurricane Fabian on consecutive days. They're based on dropsonde and Doppler radar data. The shading is the mean azimuthal wind, and the arrows and the contours show the radial and vertical flow. So there's quite a bit of variation between the 3 days, but we see in the middle one perhaps is the most classic picture. The zero radial flow line is sloping downwards towards the centre of the storm, strong inflow near the surface, and then the inflow turns through this azimuthal wind maximum and flows outwards and upwards into the eye wall. We see perhaps less outflow in this case on the second, and the storm is weakening somewhat on the fourth, and we see less outflow there also. Similar diagrams for Hurricane Isabel, which was somewhat more intense than Fabian. Again, 3 consecutive days, also from Michael Bell's paper. Very strong inflow near the surface, downward sloping top to the inflow layer, and the flow turning and descending up into the eye wall. Pretty much in all 3 cases, and regardless of where the radius of maximum wind was, there was some variation from day to day. And here's a composite figure from, this is a composite across many storms by Zhang Zhang, who's Hurricane Research Division. And so we have the azimuthal wind. These are normalised by the radius of maximum wind, so 1 is the radius of maximum winds. That very marked maximum in here at about 800 metres, which is marked by the position of the cross here, so it falls within the inflow layer. Inflow maximum close to the radius of maximum winds. And something we haven't talked about yet, but we'll come to tomorrow, is the temperature structure in the boundary layer. And this is actually very interesting and subject to a bit of my current research. So potential temperature, normally you would expect this inflow layer has got quite strong wind shear, so should have strong mixing. On average, the sea surface temperature is a little bit warmer, 1 or 2 degrees warmer than the air, so you expect to get some extra mixing from thermal convection. And so you'd expect theta to be almost constant within the inflow layer, and yet we have this very surprising structure that we have a very stable theta in the top of the inflow layer. These contours are 1 Kelvin apart.
So just my guess is the humidity is related to this case?
Yes, the humidity is important. The cloud base in these, on average, is probably sitting at around 0.5 kilometre to 1 kilometre. So up here, we're probably in cloud and are seeing, essentially we're seeing a saturated adiabatic lapse rate, which is giving us an increase in theta. But nevertheless, in the subcloud layer, we still have these very stable conditions. So I think I know why, and I'll show those results tomorrow. They're not published yet. So just to, I've talked a lot about aircraft observations, and I'd just like to introduce you to the Orion P3s used by the Hurricane Research Division. So this is one of them. I'm not sure which one they are. They're called Miss Piggy and Kermit, and I'm not sure whether this is Miss Piggy or Kermit. The P3, it's a turboprop aircraft, 4 engines. 4 engines is a very good idea when you fly into a hurricane because they have had engine failures in the past. They're actually a very old design. They're based on the Lockheed Electra passenger aircraft of the 1950s, but they've been a very robust design, and these have survived very well. They have a large number of special things on, some of which are apparent here. This is the what they call the BAT probe. BAT stands for Best Atmospheric Turbulence. So this enables them to do direct measurements of turbulent fluxes from the aircraft. The other thing you can see here is this bulge on the belly of the plane. That's a radar, so that's a C-band radar, and if you've seen reflectivity images from the reconnaissance aircraft, they're almost certainly from this. So it's a horizontally scanning vertical axis dish that's tucked away in this radar. I should say these photos came from Frank Marks, who's the director of Hurricane Research Division. I'm grateful to him for giving them to me. So here's the P3 in flight. The other thing you'll notice is there's this rather strange looking thing hanging off the tail of it. This is another radar. This is an X-band Doppler radar, and unlike most radars where the axis is vertical and so it scans like this, in this one the axis is horizontal and so it scans like that. And it's quite a clever instrument because it can vary from looking forward to back. So when it's pointed slightly forwards, it scans a series of cones, let's see if I can do this, that are in that orientation, or it can point slightly backwards and scan a series of cones like that. And if it alternates between forward and aft scanning, you get views of the same piece of the atmosphere from two directions, and so you can do dual Doppler analyses of the winds. It took Hurricane Research Division a long time to get the wind retrieval algorithm working properly and automated, but they've now succeeded in doing that, and there's a large amount of dual Doppler radar available on their website if you want to use it for research purposes.
Jake, have you ever experienced reconnaissance flight?
No, I haven't. One day I would like to. Unfortunately, when I've been in Florida, it's mostly been in around April in association with the Hurricanes Conference. So and they're not flying at that time of year. So I've said some of these things. One of the other important instruments is the step frequency microwave radiometer. So that's a passive microwave radiometer which has 6 frequencies. The ocean emissivity depends on the whitecap fraction, which depends on the wind speed. And so this has been extensively calibrated against dropsonde and buoy data. They started working on this instrument back in the 1980s, but it wasn't until they got the dropsonde that they really had enough truth to validate it properly. The dropsonde is essentially like a radio sonde with GPS measurements in it, and it's deployed from the aircraft down near the surface. The vertical resolution is about 6 metres. I think it's fair to say it's absolutely revolutionised the way we look at the boundary layer, and from the very first observations we saw, the ones in Guillermo, they've completely changed our thinking. The other thing that I should say is that NOAA and Hurricane Research Division are extremely generous with their data, and you can download it from their website. You have to sign a little agreement, but nearly all of the data that they collect can be downloaded from the website. It's a fantastic resource for research because there is decades worth of data available there, particularly in the last 10 to 15 years when they've had the dropsonde and the Doppler radar available. There is tremendous data there, and it's a very good opportunity to validate models, to try and decide whether the interesting things you're seeing in models are real. It's a good opportunity to do analyses, and if you're interested in data assimilation, it's perhaps a good opportunity to do some experiments with inner core data assimilation. So I know I started using this data a little over 10 years ago, and every time I see Frank Marks, he says to me, "Jeff, you're using more of our data. Please use our data. We love it. We love it when people use our data." And I've said, "Oh, am I allowed to tell other people that?" And he says, "Yes, please." So I'm telling you all that if you're interested in doing some research on observation-based research, perhaps rather than model-based research, have a look at this website and browse around and find some data. You'll also find that Frank and the people at HRD are quite willing to be helpful. If you're having trouble interpreting the data, they can explain it to you, and they do make some software available to help read it. So everyone should write one observational paper at least in their life, and this is your opportunity.
Is this data is used for the operational model or something to make initial condition or something?
Yes, it is used in operational assimilation now, but usually at reduced vertical resolution. So this is just a photo of, this is the drop sonde workstation inside the P3, and this is a drop sonde that's being prepared for launch. It's not in the photo, but just here there is an airlock that goes through the floor of the plane where they release the sonde. And here's the computer workstation and the electronics that's used to receive the data. So that's the end of the first chapter. Just to summarise a couple of points, there's often this strong low-level wind maximum, which we'll explore more in the next session. Strong inflow near the surface, decreasing aloft with a maximum updraft at the eye wall. There's a significant amount of variation both within storms and between storms, and we see a logarithmic profile near the surface. So I think it's another good moment to stop for a bit of discussion, and I'm going to grab a little drink of water too, because I've been talking for an hour.
Thank you, Jeff. So any question or comment? It's a discussion time.
The reason for the outro just at the top of the boundary layer, outro.
Yes.
Could you tell me the reason for the outro just top of the boundary layer?
Okay, that's in the next talk. That's a very good question.
Another question is why the location of the maximum wind speed is just inside of the inflow boundary?
That's another very good question, and I think I'm going to hold that one over to the next talk as well. That's good. I'm happy to hear these questions. That means I've prepared with a good order.
Any other question related to the next talk of Jeff?
Yeah. So the maximum winds are usually at about 80% of the depth of the inflow layer. And that's quite important implications for the dynamics of the storm. Can you hear me if I don't use the microphone? Or,
Yes.
yeah, because it's a little
It's
a little
Yeah.
easier if I don't have to. Would anyone else like to ask a question?
So so Sawada-san asked you, this kind of drop zone data are used for operational use, but I think it means they're operational forecast by Hurricane Research Division, right?
Yes, that's right.
There are, in Japan, JMA only has operational works, but maybe in the United States, several institutes conduct the operational works. So just I like to clarify.
Yes, no, that's a good clarification. They go out on the GTS as in the same code as, so the PPAA, PPBB code that radio sonde measurements are transmitted in. Probably for most centres, it's the environmental reconnaissance missions that are the most useful for simulation purposes. The ability of the model to resolve the gradients in a tropical cyclone means that the unicore observations are less useful.
Jeff, I'd like to have one break in the first 3-hour lecture.
Yes.
Do you think when is a good time? Now or 30 or 1 hour later?
Maybe in 1 hour later.
Okay.
Yeah. Oh, the other thing I'll say is I'm going to make these presentations available. So, you know, I notice some of you taking notes, which is terrific. But if there are references to other papers or things, I'll put these. I'll make them available to you somehow. Perhaps Yoshi can put them on a website or something, or I can put them on my website back at home. I will remove 2 or 3 slides from that because there are a couple of things that are not published yet and are work in progress, and I might change the results a little bit as I get them towards publication. But nearly everything you see I'll be able to hand out afterwards. So yeah, don't feel you have to write everything down.
All right. I can upload your presentation after this seminar, so I don't want anything.
Okay. Yeah. It might actually be easiest if I put them online on the website and I can send you the link and you email it around everybody, whichever way. So we're now going to have a look at the dynamics of the boundary layer. So we saw in the opening that turbulence timescales are quite short, less than an hour. But the timescale over which a tropical cyclone changes structure is relatively slow. Even in cases of rapid intensification, it's several hours before you see major change, and more typically it's a day or 2. So it's reasonable to assume, therefore, that the boundary layer is close to being in equilibrium with the conditions imposed by the rest of the storm. And that's consistent with how we think of the boundary layer elsewhere in the atmosphere. We often regard the boundary layer as being essentially a passive response to the gradient wind speed and the thermal structure at the top of the boundary layer and the surface conditions. So we'll do the same for tropical cyclones, and we'll come back a little bit later and justify this decision a little. So gradient wind and stability structure locked at surface. We have the roughness of the sea surface, and we have the air sea fluxes of the sea surface. Now, the boundary layer, if you think of a tropical cyclone as being in 2 pieces, you have the boundary layer and you have everything above the boundary layer. Everything above certainly affects what's going on in the boundary layer because the structure above defines the surface pressure field through the hydrostatic equation, and it defines the gradient wind at the top of the boundary layer. And so that's an influence on the boundary layer. But there is also a feedback the other way, because as we shall see, the boundary layer defines where the strongest surface convergence is, and it defines the location of the on-wall updraft. And so what you have in a tropical cyclone is you have feedback from the cyclone to the boundary layer, and the influence from the boundary layer back to the cyclone. So what we're going to do in this viewpoint is we're essentially going to look at just one side of the 2-way interaction. We're going to look at how the cyclone affects the boundary layer, and we're going to plot the cyclone fixed. These sort of approaches have been quite successful in boundary layer theory. The principal exceptions when they don't work are when you have very strong horizontal advection. So if you have a very sharp gradients in surface properties and get internal boundary layers, then it's not really steady state. And it's also not steady state over land where you have very strong diurnal effects. But for a tropical cyclone out of the ocean, it's a good approach to take. So perhaps to say the same thing in pictures, here's a sea surface and a cross-section for a tropical cyclone. There is the circulating wind field. which this is a Southern Hemisphere case. Because I originally did this slide for a talk I was giving in Australia. And we have the secondary circulation. So we have inflow in the boundary layer, ascent in the eye wall of the rain bands. So forced descent into the eye and also some convective downdrafts into the boundary layer, larger radius. And so the boundary layer affects the tropical cyclone because it determines where the eye wall updraft is. It determines the thermodynamic properties of that updraft, the temperature and humidity, and perhaps it also affects the dynamic properties to some degree. But the tropical cyclone affects the boundary layer back the other way because of the pressure field. Also, if the tropical cyclone is sheared, for instance, if it's if it has a tilt to the axis, then that can impose some large-scale divergence asymmetry with extra convergence on the down tilt side and divergence on the up tilt side. The impacts of that on the boundary layer have not been studied at all, so that's an open research question. The tropical cyclone can also affect the boundary layer thermodynamics, particularly through convective downdrafts. And so for our modelling, we're going to ignore this side of the interaction and we're going to keep some of this side. So the equations of motion, which are in cylindrical coordinates, and I'm sure you are very familiar with. So U is the radial flow, V is the tangential flow or the azimuthal flow. So we have two momentum equations and a continuity equation, and we can also add the hydrostatic or vertical velocity equation depending on whether we're non-hydrostatic or not. The only thing that's perhaps a little bit different is the radial pressure gradient, which I could have written as 1 on rho dpdr. I have instead written in terms of the gradient wind. And so I've just substituted the gradient wind equation into the pressure gradient. For boundary layer studies, we're often looking at perturbations to the gradient wind, so this is a convenient way to look. The frictional terms, I've parameterised those by a velocity flux gradient relationship. So K is the turbulent diffusivity. Yes, I would have written those as Reynolds averaged terms, flux divergence, but for all practical purposes, we tend to think in terms of the diffusivity. And so those equations are a large part of our model of the tropical cyclone boundary layer. If we add a pressure field or a gradient wind field from, say, a parametric model or from observations or even from a numerical, from a WRF simulation or something, to give us this term, we've actually got our model. What we then have to do, of course, is to find solutions to that model. And there are many ways that have been done over the years. And these are in rough order of reverse complexity. We can use the full nonlinear models and include asymmetries, which is what my model with Yuqing Wang does. Another option is to linearise the equations and retain the asymmetry, and that was first done for the symmetric storm by Stan Rosenthal, who was a former director of Hurricane Research Division back in 1962, or paper by me in 2001. Another very popular approach has been to say, well, these equations are somewhat difficult to deal with, and the turbulent term is one of the most difficult, so if we vertically average the equations, the vertical integral actually turns this, we take the integral with respect to height over the boundary layer, and it turns it into the surface on top of the boundary layer conditions. And so it simplifies the equations considerably. Those are called slab models or depth average models, and they've been very popular. The paper by Lloyd Shapiro in 1983 is a very influential paper. I'm of the view that they're less successful. Those models are less good nowadays. They've actually been used a lot in the United States for engineering design purposes, but I think there are problems. Symmetric versions of those, Roger Smith's used them a bit. If you linearise that model, then you get a very simple model, which I'll talk about briefly later on, which was first used by Vikuyama in his famous 1969 paper, the three-level model. The lowest level was this form. And it also becomes the boundary layer part of Kerry-Emanuel's potential intensity theory. Or you can say that depth averaging is a bit of a severe approximation. Perhaps if we imposed a vertical structure that looked say something like an Ekman layer and solved the equations that way, that would be more accurate. That was first done by Roger Smith in 1968 and Kuo in 71 and also by me a few years ago. We won't talk very much about these. And then the simplest of the lot that you simply assume a column model, as is often used in boundary layer studies, and a couple of examples of that. Nearly all of these, in fact I think every one I've listed studies the response to an imposed steady tropical cyclone-like pressure field. There are a very few studies which have looked at the spin down of vortices as a way of studying the boundary layer, but the majority impose a pressure field and study the response to that. A couple more ideas which I'm sure you're familiar with, but just to make sure we'll go through them. Here's the V equation. It's often quite convenient to write this equation in terms of absolute angular momentum. So if you define absolute angular momentum as RV plus half FR squared, because you've got a term in the angular momentum due to the Earth's rotation, then this equation simplifies down to here. And you'll see there are a worthwhile simplification is that we've got rid of the Coriolis term. And it's customary at this point to make a couple of extra simplifications. One is to assume that the axisymmetry, which gets rid of a couple more terms. And if you also assume that it's frictionless, we get an equation which basically says that the material derivative of angular momentum is zero. So angular momentum is conserved following the vortex. People don't write models in terms of this, but it's a very good tool for interpreting model results. So the full model, which we're going to talk about for this chapter, we solve the thermodynamic and momentum budget equations over a domain that's hundreds of kilometres across and just 2 or 3 kilometres deep. The upper boundary condition represents all the effects of the tropical cyclone on the boundary layer, and the important one is that we have that enclosed pressure field. We also have a storm motion. Usually we make a coordinate transformation, so we work in a coordinate system that's moving with the storm, and so we have the Earth's surface moving past underneath the storm. And we have we don't have environmental asymmetries at present, but we do have the motion asymmetry. The lower boundary condition in the model, we have a SE interaction parameterization, the sort of thing that you'd see in a Wolf type model, or the NHM or our UM. In between we have a turbulence closure, and there's now about 10 different turbulence closures sitting in the model because I did a bit of research on that a couple of years ago. And full description of the model is in these two places. So let's look at what we actually see from the model. So here's a height up to 2 kilometres, radius out to 200 kilometres. The colour is the azimuthal flow, and the little magenta arrows, which slightly clumsy way of drawing it, but give you the idea. They show the radial and vertical flow. And they look quite like the observations. We have this strong inflow near the surface, the rapid turning of the inflow near the radius of maximum winds, and the ascent in the eyeball. We have the top of the inflow layer is a little bit hard to see on here. I've got another figure on the next slide which shows it more clearly. But you can see there's this maximum, the maximum in the azimuthal flow increases with radius it increases as you go outwards in radius. The gradient wind is essentially constant throughout the domain, so the fact that we've got the wind maximum down here at sort of about 500 or 600 metres, increasing up to about a kilometre up here, and that the wind there reduces with height, suggests that these winds are supergradient. They're stronger than you would get from the gradient wind equation. This is the same simulation but plotted slightly differently. So we have the radial component, inflow with the outflow aloft. We have the azimuthal component, and we have the vertical flow with this, we get this very marked updraft near the radius of maximum winds.
So did you impose any boundary condition for vertical wind speed?
The vertical wind speed doesn't have a boundary condition, that's just calculated from the continuity equation. The upper boundary condition on velocity is that the vertical derivative of the velocity is zero. So it's essentially a zero flux condition, and the top of the domain is a little bit higher, it's about